Okay, hello. We are moving on to chapter 11 now, and this chapter is called Vector Calculus. We've been interacting with vectors a little bit, and now we're really pushing into this idea of calculus a little bit more. As a fun fact, since I know we're all chemists here, this word calculus is related to calcium, same root, calc. I mean, I'm sure you've heard calculator as well. But actually the root is Latin in origin for either little stone or pebble. As you can imagine, calcium is very common in a lot of little stones and pebbles as an element. But calculus, how does that relate to little stone or pebble? In fact, calculus, as mathematics, arises from the use of the abacus. Since the pieces were pebbles. Or even you would be counting stones even independent of an abacus, right? If you wanted to count a lot, you would throw a bunch of stones on the ground and separate them into piles. So that's actually where our word calculus comes from, so that's kind of cool. Interestingly, this word calculus also does have a true meaning of little stone or pebble. You may hear your doctors or dentists refer to a calculus somewhere in your body. Ideally they don't, but that's in those cases when you would develop kidney stones or gallstones or even something on your teeth, little stones or tonsil stones, etc. So that's the other version of calculus. But of course today we're working with our calculus, which I think is very commonly assumed to be derivatives and integrals, right? So we're looking at different forms of derivatives. We were able to take derivatives of curves in the last section, but now we're moving on to derivatives of vector fields and of scalar fields. So let's look at that really quick. So they're calling it the gradient of a scalar field here, and this is maybe a new word for you, maybe not. I mean, gradient, of course, has a colloquial meaning. The colloquial meaning is the gradient of a slope of a hill or something, right? If you're hiking, then you talk about the gradient of the hike. And this is kind of the same idea. So turns out in British English, they always call gradients slopes gradients and vice versa. Slope is always gradients in math. So even, in high school, middle school algebra, when you talk about slopes of curves, that's in British English, it's always referred to as gradients. So you can think about this as being the slope of the vector field, and just as we were calculating derivatives to get slopes in calculus 1, really all this is the derivative in a way which makes sense of a scalar field. So you can't quite just take a derivative of a scalar field because there's multiple directions to calculate a slope in, and that's why we use this word gradient. It encapsulates all of the directions at once. All right, so here's our directional derivative, and we were actually calculating this before in the previous problem with the limit quotient. But in this case, we can actually calculate the directional derivative. Here, this is the normalized. Okay, so that means it's unit vector in the direction we want to find slope in. So that the n is going to be the unit vector in which the direction we want to find slope in. And then we have this funky thing right here. That's this symbol. The symbol upside down delta. The author puts a vector arrow over it, is called nabla. Don't ask me the etymology on that one. I don't actually know it. Maybe I'll look it up for you later. It's called nabla. You can also call it grad. Ideally, grad makes a lot of sense as to why we would call it grad when this is referring to the gradient and refers to the gradient of the vector field F. So what we're doing is we're going to find a directional derivative, which is the same notation we found earlier. We're going to calculate a unit vector in the direction we care about, and we're going to dot product that with this thing called the gradient. So let's define the gradient for you really quick. It's defined as a vector partial derivative in each direction. And I know you had a homework problem on this as well already, but it's defined by the vector, which is the partial derivative in each direction in that vector. Okay, let's move on then. So because of all of that, you can see if we wanted to calculate partial derivative with respect to x, we could just take the gradient and multiply by this vector, this x vector, recall, gets defined as 1, 0, 0. So that's our x vector, and that would extract the partial derivative with respect to x for us. Okay, so there's our definition of the gradient at a point again. I did just define that for you. And a lot of times we'll consider, this is some people say this is bad notation. I don't agree, but some people will. You can consider the gradient itself as a vector, in which case you're performing this idea here on f is considered right scalar multiplication by f. It's like I was multiplying this vector of nabla on the right hand side by f, and then the derivatives act on f and give me my gradient above. I think it's perfectly fine notation. Some people don't like it, but let's just keep that in mind that we can consider it as a vector itself. And now let's actually compute the gradient of a scalar field. So here's a nice function. It's actually the same function we encountered earlier in a previous section, but let's compute the gradient. So I'll mention over here, to compute nabla, we need partial f partial x, partial f partial y, partial f partial z. So let's compute those. I'm going to compute them up to the left here. And we saw this from the previous section, so I'm going to go through it relatively quickly. You've had some practice with this now. Partial f partial x is going to give me yz cosine xyz plus 1 plus 6xz. Partial f partial y is going to give me xz cosine xyz plus 4y. And finally, partial f partial z is going to give me xy cosine xyz plus 3x squared. Okay, so from this, how could we compute the gradient now that we have all three of them? It's actually much easier than you might think initially. What I'm going to do is put all three of these into a vector together. And there you go. There's my gradient. I can say this is equal to gradient of f. Okay, we have some rules for the gradient. They're going to behave a lot like derivatives, but they're outputting vectors. So we just have to keep in mind that we're going to gain a vector field out of a scalar field. That's one thing maybe I should note here. Nabla as a map maps scalar fields to vector fields. Just something to keep in mind. Okay, so our rules, we have the sum rule, pretty standard for derivatives. We can split it over sums. We have the constant multiple rules where the constant multiple can pull outside, right? It's kind of pulling outside of my derivative. Finally, the product rule is particularly useful here. So it maybe wouldn't seem too natural that the gradient, which produces a vector field of two scalars multiplied together, is actually equivalent to the vector field computed from one scalar times with scalar multiplication of the other scalar field on the outside, and then you add vice versa. So maybe this wouldn't be initially clear, but it makes intuitive sense when we think about this as a derivative that we're going to obey the product rule. So that's just useful to keep in mind. All right, so the paraboloid is not too difficult to calculate gradients of, right? Because the partial with respect to x is going to give me 2x, and the partial with respect to y is going to give me 2y, so the gradient is very clearly 2x comma 2y. But the nice thing here is that if we look at level curves, so that's what's special about this example. If we look at level curves of this scalar field, and then we plot the gradients as vectors, the gradient vectors always point perpendicular to level curves. So we can see that over here. This arrow is pointing exactly perpendicular to the level curve, and no matter where I look, the same behavior occurs. So that's a really nice fact about the gradient, and it makes sense if we think about this topographically. You can imagine if we were viewing a mountain from above, and we asked ourselves, what is the gradient, what is the slope of the mountain at any given point? Well, we would calculate that by moving perpendicular to the change, or to the flat direction of the mountain. If the mountain's staying flat in one direction, the slope is exactly perpendicular to that direction. So that's really, really a nice thing to keep in mind about gradients. In particular, it points uphill, right? So the slope would get defined either up or down the mountain. We've chosen to define it in the way that defines it uphill. But you could, of course, add negative signs, and that would point it downhill. Okay, now this gives us something very, very special. So let's think about, so we're just going to peek at the bottom there, optimization. Let's think about this paraboloid case over here and recall what the paraboloid actually looks like. The paraboloid looks like this. Let's grab a different color. The paraboloid looks like that shape, right? It's a cup that's pointing upwards. Now you can imagine, this is the coolest thing about optimization with gradients. Let's ask ourselves the question, where is the gradient pointing at the minimum? Even same right there. In which direction is there a slope? And the answer is nowhere. Gradient doesn't point in any direction, which is equivalent. Hence, gradient f equals 0 at the minimum. And this should feel just like calculus 1 to you, right? If we wanted to calculate the minimum of a curve, we would take a derivative and calculate where it's equal to 0. This gradient really serves like the derivative to us. And so we're going to calculate where it's equal to 0. That's going to give us mins or maxes, right? Or max. And these are local, just like in calculus 1. Well, that's really useful, okay? So let's jump down to this optimization term. So in single variable calculus, we calculated it as the following. But now with the gradient, we're going to do the same thing. So we use this special language to calculate that. We call it a stationary point. And that's just specifically the point that's going to be either a local min or a local max, or possibly what we like to call saddle points. So these are the points at which the gradient is equal to 0. And we can actually calculate second derivatives. This is the higher dimensional version of the second derivative test. In higher dimension. So the higher dimensional version of the second derivative test says, hey, if we're concave down in both directions, a concave down function in two directions is going to look like that, right? There's maybe my y direction, there's my x direction. So the point in the middle of this concave down situation is definitely going to be a local maximum. Maybe I'll add these words in there. Local, just so that we keep those in mind. It's going to be a local maximum if they both point down, or concavity, and then if they both point up, like we saw on the paraboloid, then we're going to gain a local maximum. So maybe there and there. There's my x and y directions for my paraboloid. And then this idea of saddle point, if otherwise. Now, why would we call it a saddle point? Why do you suppose we call it a saddle point? Well, let's take x to be concave up. Now let's take y to be concave down. And let's actually connect these with lines that actually make sense. So what this would look like if we connected all these lines properly, is we would get a shape which kind of looks like this, and then let's see, in this direction it would come out like this. I'm trying to make this look like a saddle for you. This comes through, goes backside there. All right, ideally that looks like a saddle for you. I was not an art major, but that should look something like a saddle for you. That's like a saddle that you're riding a horse on, right? The rest of the horse is over here. There's its tail. Okay, so you can imagine you're sitting on a saddle for a saddle point. So yes, mathematicians are very clever when they name things. All right, so this is going to be a nice exercise for us. Let's grab the following function and find some stationary points. So to do this, i.e., what does it mean to find a stationary point? Find where nabla f equals 0. Well, to do that, we're going to have to calculate some derivatives. So let's calculate nabla f. And now the quotient rule is no fun, but we'll just have to go through it. So partial f, we're going to do bottom, derivative of the top minus the top, derivative of the bottom gives me a 2x. And the same thing with y. Thankfully we're symmetric, so we can just replace every y with an x and every x with a y in the above. Make our lives easy. And if I wanted to simplify this a little bit, ideally everybody has noticed that my e to the x squared plus y squared is in every term. So those are all going to cancel. And really what's happening is we have 2y squared x minus 2y squared x minus x and 2x squared y minus y. So I'm going to erase all of these and replace them with a simplified version. I'm going to simplify all these terms a little bit. So it's going to look like, so it was 2x squared minus 1 y, and this was 2y squared minus 1 x. And from this, it's pretty easy to find our stationary points because we set this equal to 0, 0, and we're going to solve each equation individually. So 2x squared minus 1, y equals 0. When does this equal 0? Definitely when y is equal to 0, or when x squared equals 1/2, which is the same as x equals 1 over root 2. And in the second case, we have the opposite. 2y squared minus 1x equals 0 in the opposite, when x is 0, or when y is 1 over root 2. These are plus or minus, right? Because we're taking square roots. Okay, so this is actually a little bit unclear right now. How do these give us our stationary points? Well, it's all combinations of these. All right, now we're going to go to part B and the whiteboard for the specific case of x being 1 over root 2 and y being 1 over root 2. At the whiteboard, we determine max or min at 1 over root 2, 1 over root 2. For, now we'll recall what nabla f was. It was 2x squared minus 1y, 2y squared minus 1x. And so to determine this at this point, we need to calculate the second derivatives. So second derivative of y with respect to x is going to be the first derivative with respect to x of the one we've already calculated, which was 2x minus 1y. That's going to give me 4xy. Now if I calculate this at 1 over root 2, 1 over root 2, I'm going to end up with 2. 2 is positive, so we're concave up. That direction in x. We need the same to be true in y. So let's see. Partial squared f, partial y squared is partial y, 2y squared minus 1x. And that's going to give me 4xy yet again, which at 1 over root 2 is equal to 2 as well. So we are also concave up in y. Okay, so if we're concave up in both directions, that's very clear about if I'm a min or max, thus a maximum. We could calculate the saddle point there, but we're not going to. And then there's an extra cool thing about optimization that's called Lagrange multipliers. And it turns out we're not going to be talking about them for now in this class, but if you're really interested, I can describe these in class for you. All right, and that's all I have. Thanks very much. See you in class.